Start recording. All right. So in contrast to exam 1, exam 2 actually is much more well suited for an online examination. So I'm actually pulling it up on my side right now. Exam 2, where are you? There it is. So exam 2 has a lot of the questions are multiple choice, fill in the blank. They're designed. A lot of the questions are designed so that you can easily they'll easily be auto graded. And then that leaves just the few coding questions for me to grade. There's going to be in total 2 questions back to back on programming for trees, where you have to write methods that handle trees. And then finally one question on doing maps. But it should be very, very simple. That one should be fairly simple because it's something I've done in the lecture videos. In total 45 points of the exam are basically programming questions. Okay, 45 points are programming. The rest is multiple choice and the like. And I'll point out where the analogs are as we go through the exams so that you know what to expect. Okay. And as with the previous exam, it is open book, open note, open internet. So you know. So just with the restrictions of, please don't, go on Fiverr and pay somebody else to take your exam for you. All right. So, first off, data structures over here. So you will get a question like this during the exam as well as during the final exam. Now, as far as online exams, as far as this is concerned, when you actually take the exam, these will all be multiple choice questions instead. So I'll give you 4 choices and you need to pick the correct one. Okay? So let's go ahead and go through these. So you need to model which patient should be seen next at a hospital. Patients should be seen in as close to the order of arrival, but patients with this more severe situation should be seen first. So which data structure is best for modeling that?
Priority queue.
That's right, a priority queue. That's the entire point of triage, by the way, which is to see who is sick and who needs treatment first, right? It doesn't matter that you've been waiting. Yes, you've got a broken wrist. That sucks. It's painful, and you should not be in pain, and you really should not be in that much pain. But
For example, somebody comes in with a pulmonary embolism.
Yeah, that's probably a bit more important. Or that baby with a 38 degrees Celsius fever, which is or above 38 degrees Celsius, which is above 100.4 Fahrenheit. That needs to be seen. So there's all these so that's the entire point of triage. Now you'll be seen before the guy who came in after you who also has a broken wrist. But you got to be but the entire point of a priority queue is to make sure that people get seen in an appropriate order, or things get taken care of in an appropriate order. It's a queue that allows some cutting based on relative importance. And now I'm trying to find my pen. Hold on. Got knocked down. Alright, so next, a router needs to hold packets in a buffer and deal with them in the order they appear. Which data structure is that?
A queue.
That is a queue. That is actually a classic example of a queue, a buffer, where basically, right? So, a real world example of this is in network architecture, where your router is receiving information, and when your router, when it receives information, needs to process. It's not just like passing it out in one direction, right? There's multiple devices plugged into a router. So it creates a queue, and it goes through each packet and says, okay, I'm going to send this one over here. I'm going to send this one over here. I'm going to send this one over here. Now it goes through it much, much faster than I could do it, but it's just a queue. Next, you need to model a hierarchy. So,
Tree.
Yep, a tree. Anything where there's this kind of top-down approach uses a tree. Now,
Priority queues. Which lectures are they covered in?
those are
The
covered in the
heaps.
heaps.
Okay, cool.
Okay. Now, you need a data structure to hold your previous decisions in case you need to backtrack.
Stack.
Right. Recursion is not a data structure, and I always get at least one student who gives me that response. So, but it's a stack. You use a stack to hold previous decisions. All right. So next for this guy, this is actually on the exam. It's actually closer around 10 points than 6 points. First off, and there's a lot, and it's a bunch of fill in the blank questions, just like you had on the quizzes for binary search trees. And what it is it will be. Let me go ahead and see if I can't find a picture, right? So it's going to be like that quiz you took where I give you a picture of a tree and I ask you, hey, tell me what the relationship between these two nodes are, or something like that. So, let me go ahead and see. Yeah, that's one of my documents for creating trees.
Are you going to spend way too much in LaTeX? Way too much time in LaTeX doing it again?
Not anymore. Now that it only took a lot of time to figure it out for the first time. Right? So figuring it out the first time was a pain. Second time, not so much. Right? So here, it will be the questions will be a lot more like the ones you get on the quiz, where basically there's a tree. It's going to be the same tree each time. I just repeat it so you don't have to scroll up. Okay? But it's going to be the same tree each time, and I'll basically ask you, hey, what's the relationship between nodes B and I? Right? Node B is the blank of I, right? And I'll try to make it there. If you have a spelling issue, then I'll correct that manually, but otherwise, I try to catch all the common terms. One question that so let's see. But if you can do this page, you'll probably be fine. So the node at the top of the tree is called a what?
The root.
Yep. It is the root. Okay? The links from a node to a successor are called what? Anyone?
Branch?
Branches. I'll also accept what? What also would be acceptable? Anyone? Something maybe from graph terminology?
Edge?
Edge is acceptable. As well as link. Because recursive definitions are a thing. Right? The predecessor of a node is called, in a tree, is called a what?
Parent.
A parent, also called a predecessor. If I'm
That's
general,
the question, though.
I know. If it's more generalized, if we were to, what's the generalization of a parent?
Ancestor.
Ancestor, right? Your parents' parent, your parents' parents' parents. Although if you say grandparent, then I'll know what you're talking about because that's perfectly fine to use in tree terminology. What are nodes that have the same parent?
Siblings.
Siblings, right? And what is your? And let's go ahead and draw this situation, right? Rather than trying to describe it. So here. Sorry, let me go ahead. Let me draw a bit bigger. So what is the relationship between nodes A and B? How would you define that?
Aunt or uncle?
Aunt or uncle. That is the appropriate term, aunt or uncle, because there's no gender neutral term for aunt or uncle in English, as far as I know. But here, and you might wonder where that's relevant. It's relevant in some algorithms that balance binary search trees, but using family tree definitions they're fairly good. Although it does get confusing if you do refer to your second cousin once removed, so be aware of that. So let's go ahead. Describe without using code how to calculate the height of a tree recursively. Now, I'll also mention here that there are differing opinions about what the height of a tree is. Some classes will define, and some contexts will define. So first off, whoops. Let's draw a tree of height 3, shall we? This is a tree of height 3. Okay? Although some places would say this is a tree of height 2. Because starting at 0. And it just depends on the class, but I think that it makes more sense to call this a tree of height 3, so we do so.
So that's the definition that we'll be going with then.
Mm-hmm. So, how would you find the height of this tree recursively?
Okay. So starting at the beginning, start a count at 0.
Mm-hmm.
Start a count at 1 at the root node. If it has a left child, count the left subtree with and increase the count by 1 when you call that.
By 1? Well, it's not that you increase it by 1. The height of a tree, right, is you got to turn it into a local decision, right? Which is the height of a tree is equal to the size of its left tree. Sorry, the bigger of the left or of the height of the left or right tree. Okay.
Okay.
And then add 1 to it. So it's 1 plus the bigger of the left or right tree height.
Okay.
So if we were to do that in code, it would be something like return math.max. Sorry, that's a lowercase m. Math.max. Math.max, by the way, useful function, which just simply says give me the bigger of height, height left, comma, height right, plus 1. Make sense?
Okay.
Although again, my handwriting's illegible. But it's basically, how do you find it? Figure out which is the bigger of your left or right subtree. Your height is 1 plus that number. It's actually a rather short algorithm to write. Now, this question over here it gets folded into the next this section on the exam, the previous section on the exam. So, the tree definition part. So, that's where the other points come from. I do say to use a different example for each binary tree because if you didn't, this is a valid answer for each of them. Right? This guy is full. Why is this guy full?
Because he has either 0 or 2 children.
Right. He has this tree is made up of nodes that either have 0 or 2 children. Okay? This guy is perfect. What makes him perfect? Well, he's in a tree of h height with exactly 2 to the h minus 1 nodes. That's what the mathematical definition for perfect is. The mathematical definition for perfect is you've got some tree of h height with 2 to the h minus 1 nodes. So if we were to do a perfect tree of height 2, it looks like this. 2 squared minus 1, so that's 3 nodes. And it just so happens that it looks like this, right, for the next one. Right? Basically, a perfect tree is a tree with all of its some height where all the levels are filled. And all the spots for nodes are completely filled. Make sense?
Mm-hmm.
A complete tree, on the other hand, is the one that is possibly the most annoying, especially because it doesn't do a recursive definition. It says, hey, it's perfect so it's a tree of height h that's perfect for the first h minus 1 levels. But the bottom level, it's not perfect. It's instead filled up from left to right to some point without any gaps. So this is a complete tree over here. This is still a complete tree. But this is no longer a complete tree. Notice that there's a gap right here. Okay? There's a gap going from left to right. Does that make sense?
Mm-hmm.
More examples. Okay. So more examples. This is not complete. We've got a very large gap. This is complete. This is also complete. But if I put a node anywhere but here, it's not going to be complete. It's got to be filled in left to right on the bottom. And of course, if it's not perfect on top, it's not going to be complete. So if I were to do 2 different examples, I would say, hey, here's an example of a full tree. This is full. This guy is complete. And then this guy he also happens to be full, right? And then a perfect tree, I'll just be lazy and draw this. Now, of course, I won't make you actually draw anything on the exam, because that would be kind of difficult. But if you feel the need to draw, just snap a picture of it and you can upload it at the end of the exam. Okay. Alright, draw the binary search tree that forms after inserting the following integers. So, normally on the exam, again, I'd have you draw this out, but because that's tricky and file uploading can have issues, this is a multiple choice question, just like on the other one where I will, here's the tree, please show me what happens after we insert this number. Make sense?
Mm-hmm.
Okay. Annotate. So let's go ahead and build this tree from scratch, though, just to make sure we understand. 42. So 10 is less than 42, so we add 10 to the left. 10 goes over here. 50 is greater than 42, so it goes to the right. 12 is less than 42 but greater than 10, so 12 is going to go over here. Now, 17, less than 42 but greater than 10 and 12, so 17 goes over here. 80 is greater than everything, so it goes all the way to the right. And negative 12 is going to go over here. 100 is going to be over here. And 96 is going to be greater, 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 less than, so 96 goes over here. 105 is greater, so it goes over here. Okay, next is 86, which goes, let's see, 86 is greater, 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 greater than 80, less than this, less than this, less than this. Okay. And now 72, right? 72 is greater, greater, less than, 72 goes over here. Make sense to everybody? For a binary search tree, at every point, all the smaller items are on the left, and all the greater items are on the right. All right, so the next question, using your previous answer, draw what happens when you remove the following. How convenient that that stays on the screen, right? All right, first things first, we need to remove 42, right? Removal has 3 cases, which is that if the thing has no children, just delete it, because that's easy. It's gone now. If it has one child, have the grandparent adopt the child. So if we were to delete 96, as we do later on, we delete 96 and would have 100 adopt 86. Okay, and because we want to do it so that we make the least amount of changes. But with since we're deleting 42, 42 has 2 children. And we can't just simply promote 10, right? We can't. Now it works out that we can just simply move 50 up here. That doesn't always work out. But it doesn't work out that we can just grab 10 and throw them over here. That would throw a lot of this out of order. We'd still have 12 and 17 on the left side, and that wouldn't work with 10 being the root. So the root has to be replaced. It can only be replaced by one of 2 items. Its next in order predecessor or its next in order successor. To find those is very simple. You go one to the left all the way to the right to get the next in order predecessor. In other words, you're finding the biggest thing that is smaller than me. So you go one to the left to get to all, because that gets you into the left subtree, where all those things that are smaller than you are. To find the biggest thing there, you go all the way to the right. If there was something bigger, it would be to the right. If it's impossible for something to be, for you to miss it, because if you go to the right, you're going towards the bigger, where the things that are bigger are going. And if there's something to the left over here, that's smaller, so that doesn't matter. To find the in order successor, you go one to the right and all the way to the left. In this case, you stay at 50. So what we do is that so here's what we do. We will to delete 42, we go one to the left all the way to the right, and we replace 42 with 17. And then we delete the original 17, right? So we now delete 17 from the left subtree, which is right over here. And, turns out that is pretty easy to get rid of, because guess what? 17 has no children. So we just remove it. Next, we remove 12. 12 has no children. Next, we remove 17. Okay. So here, what do we do again? We go one to the left and all the way to the right. So we end up at 10. So now what we need to do is have 10 we move 10 to the top and then delete the original 10 from the left subtree. To delete the original 10 from the left subtree, that has one child, so we have 10's parent adopt the child. So remove 10.
I have a quick question.
Yes.
Do we like draw each step, or do you want us to like, or I guess we're not drawing, but like, do we just like show the final tree?
It'll be the final tree on the exam because you'll have a because it will be multiple choice.
Okay, cool.
On the actual exam, I'd want you to draw the intermediate steps. But sorry, on an actual written exam, I'd want you to draw the intermediate steps. But here, online, it makes more sense for it to be multiple choice. Right? So I will give you, like, here, draw what happens after we remove, I forget, like one or a bunch of them. So you, or like, which is the, you don't draw it, but I ask you, like, select the one that's appropriate. Okay. So which of the following is the pre-order traversal of a binary tree with subtrees tree left and tree right? So pre-order means we handle the root first, and then we do the left subtree and then the right subtree. You always, no matter what it is, you always do left and right. For a post order, you do the left, then you do the right, then you do the root. So the only thing that matters that changes is where you process the root node. In pre-order, you process it first. In post order, you process it last, and in order, you process it before everybody else. So in between everybody else. So it goes left, myself, right. There is one more traversal which we'll cover later on, which is called level order traversal. So and that one is not going to be on the exam, but it may look a bit familiar. So A, B, C, D, E, F. Okay, and level order traversal would give us A, B, C, D, E, F, which is actually breadth first search. And it's not really taught here. We don't really go over it right now because guess what? It's fairly simple, and it doesn't use recursion to do. So here, draw the min heap. Again, it will be like, here's a bunch of items. Show me, select the answer that we get with the min heap. So again, multiple choice.
Can you go over that one? I don't remember the min heap.
Min heaps are fairly straightforward, which is that basically that it has a different recursive property, which is that the root is the smallest.
Oh, right. Instead of the max heap, the min heap.
Yeah, min heap is the smallest item in the left and the right. So here we put in 8. Then the next is, and you always insert items so that it will be a complete tree. So next is 10. So now we inserted 10. There doesn't need to be a change because 8 is the smallest item, and the smallest item needs to be the root. Next we add 50. No changes needed. Next we add 20. No changes needed. Next we add 1 over here. Now 1, and how do we, so 1 needs to obviously be the root, but how does this work? How do we know? Well, again, we're making our decisions all locally. And so what I'm going to do is I'm going to compare 1 to its parent. So if my item is less than my parent, I'm going to swap. So what we do over here is that we put 10 over here and we put 1 over here. And then we just repeat. Is 1 less than its parent? Yes, it is. So we are going to put 1 on top and 8 where 1 was. So 8 and 1. And we've reached the top, so there's nothing to compare to, so we stop there. Next, we insert 4. 4 will go over here to the left of 50 because that's the next spot for a complete node. So now we compare 4 to 50, and we go, oh, well, 4 is less than 50, so we need to swap them. 4, 50. Now we compare 4 to 1. 4 is greater than 1, so it can stay put. And finally, we put in 3. 3 is less than 4, so we swap 3 and 4. So you just insert, basically, the lighter items bubble to the top in min heaps, right? You just simply say, I'm going to insert the item at the bottom in the next possible space, and if it's lighter, it bubbles up, while the heavier items fall to the bottom. Make sense?
Yep.
So it's kind of like bubble sort, like in some weird sense.
Yep.
It kind of like follows that same algorithm.
Mm-hmm. And
then why is 8 on the left side and 3 is on the right?
8 is on the left side just simply through the way things got inserted. 8 is on the left side. 8 is on the left side because 1 got inserted on the left side and it bubbled up.
Okay, so it doesn't really matter unless.
Oh yeah, left and right doesn't matter. Left and right doesn't matter. All that matters is that at each point, the root is the smallest item in the heap. So 1 is the smallest item in its heap. 8 is the smallest item in its own heap. 3 is the smallest item in the heap, in its own heap.
Okay, it's clear.
Right? 3's got its own heap. 8's got its own heap. And 1's got its own heap. Okay, now using the heap we drew above, draw a heap after removing an element twice. Now I say an element because we really only cover one way to remove nodes, which is we only remove the root in a heap. Okay, so the way that's going to work is that basically you remove the item, okay? And then you take the item in the last position, remember it's got to remain complete, and move it to the top. Okay, so we took 4 and overwrote 1, and now 1 is the root.
You mean 4 is the root?
Yeah, 4 is the root. But there's an issue with this, of course. 4 is bigger than 3, right? So it's not the smallest item. It's not at the top. So what we do here is that you move the item from the last position, move it to the root, and then you check it against both its children. And then if it's smaller than one of them, you swap it with that. Sorry, if one of the children is smaller, you swap it. If both the children is smaller, you swap it with the smaller child so that the smallest child gets to the top. So here, 4 is less than 8, so that's fine, but 4 is greater than 3, so we need to swap 4 and 3. So, let's see. Swap 4 and 3. Okay, next. Swap 3. Next, 4 fell down. To the right is nothing, so there's nothing to compare to. And to the left, 4 is less than 50, so stays put. Okay, now to remove our second element, we remove from the root. That would be removing 3. And now we replace it with 50, because 50 is the next item, is the last item there. So now we've got 50. 50 is less than 50 is greater than both 8 and 4. So it's greater than both of its children, so we're going to swap with the smaller child, so the smallest item gets to the top. Right? If we swap with 8, the smallest item would not get to the top. And now 50 has nothing else to compare to. It's hit bedrock, so to speak. So it stays put, right? the bigger items fall down whilst the smaller items bubble to the top. Huffman coding is not on the exam. I've excised it from the summer semester just simply for time constraints. Okay?
Okay.
Or at least it's not on the second exam. It might be on... I think it might be on... Yeah, it's on the final exam, but for right now, don't worry about it. If it's on the final, I might remove it. We'll see. Okay, but now we're into the coding questions, which I will not do by hand because I really wish I had a soundboard so I could throw this to the ground and have a cat yowl. Throw it to the ground, glass break, cat yowl. That sounds like it would be fun. Hey, Annie, what's Laser up to?
He's eating goldfish.
Awesome, and you're working on the puzzle again?
Yep.
Has he been helping with it?
He was, but he also was just shoving pieces all over.
Yeah.
He is
Yeah, he is 3. Alright, so with the coding, you're not going to have to suffer through my handwriting. I'll just do it in Visual Studio Code because that's quick to boot up. And let's go ahead and create a new... Let's go ahead and do a new desktop file. exam2.java. Save. Okay. And there, what we're going to do is that I'll go ahead and write my private class just to use it for Node. Private class. Private class Node. Just so that I'm not going to get any errors. Right. Class node E. That's what I wanted. E data. Node E left. Node E right. And then constructor public node E item E. You know what? I like calling it item, so I'm just going to call it item instead everywhere. Item. And now this dot item is equal to item. That's all you need to create if you wanted to test your code out, really. Well, you'd also have to create the tree. So now it says create this method. Don't use the size method. It calculates the number of nodes in the tree, right? Normally you could use something like a size method, but here we go. So let's write a recursive method to calculate the size of the tree. Okay. So the size of the tree, if you think about it, right? I'm at the root. I'm somewhere in the tree. Right? Not necessarily, it's the root of the tree or the subtree. All right. First off, it's possible that this root does not actually exist, right? So, if the root doesn't exist, if it's null, what's the size of the tree then?
0.
Boom. Return 0. Okay. Otherwise, I exist. My left child might not, my right child might not. That's their problem. They can deal with that existential crisis on their own. Okay? But I know how much I am. Okay, how big am I? 1. Me. Solitary. I am 1. Right? Now, because again, just approach this from a local decision. Okay, I am 1, but how big is my left subtree? I don't know. Let them figure it out. And how big is my right subtree? I don't know. I'll let them figure it out. Make sense? So, I am one item. Then, how big is my left subtree and my right subtree? Don't know. But I know that the size of this subtree is going to be equal to the number of nodes I am, which is 1, plus the number of nodes in my left subtree and the number of nodes in my right subtree. Right?
Mm-hmm.
So, it's a fairly straightforward method. One of the methods is that we're going to be writing is going to be fairly straightforward in the same manner, and one is going to be a bit harder. So, let's see. Write a method which, given a tree, returns whether or not the tree is full. This will be slightly different than the recursive traversal methods we've tried so far. Ah, yes. So, let's go ahead and see. What is this going to look like? Public static eBoolean is full. So, what? I don't know what to do for my default consideration. I'm just going to return... You know what? I'm going to return false for right now, and if I need to, I can change that later. And then I'm saying that honestly. I have no idea I forget what I'm going to be doing. Or I might need to remove it. We'll see. So, if tree... Let's go ahead and switch this to root. If root equals null. If I'm blank, well, I have no children or 2 children. I have no children, so I'm going to go and say return true. Sound good?
Yep.
I don't know if that's correct, but we'll find out. Okay.
I think it technically is.
I mean, it sounds like it's technically correct, which is the best kind of correct. Otherwise, right, I need to figure out how many children I have, right? Or I need to, basically, actually, now I've got 4 possible scenarios. If I have if root dot left equal null, and root dot right equals null, right? If I have no children in my left and right, then I'm full, right? This subtree is full, right?
Mm-hmm.
If on the other hand, I have, and I'll be explicit with all these. Otherwise, if I have one child, if I have a left child but not a right child, or if I have a right child but not a left child, then I'm not full, right? Because I've got a left, because I need to have either 2 children or no children. These 2 cases, I have 1 child. I have either a left child or I have a right child. Here I return true because I have no children. There's one more case, which is what if I've got both children? So this return false becomes unneeded. Else, right? If it's not any of those cases, then I am a node that exists that has 2 children. In which case, I need to figure out what my left side and my right side are. So return is full root dot left and is full root dot right. So I'm going to figure out if my left side is not a full tree, that means I'm not a full tree in general, right? Because then we exist in a state where there's a node with 1 child or no children. Make sense? If on the other hand is full returns true, then all the nodes in that subtree had either no children or 2 children, which is fantastic. So that's why this will work. next, here's extra practice. Write a method given two trees or subtrees returns whether or not the contents of the entire tree are identical. E.g., do tree A and tree B store the exact same data in the exact same way? So, not do they have the same data. If they have the same data, I would just simply do an in-order traversal of both of them and compare the outputs. Okay? Here I'm asking, basically, is the shape of the tree exactly the same?
So when you look at it that way, it's a 6. But why don't you count the fish?
So let's go ahead and grab this. We have two trees. So first off, we need to do a where do we even start with this? Good place to start is is to figure out what happens if they're null, right? Well, if tree A is null, what can we learn from that? Well, nothing in particular. But if tree B is also null, right? If they're both null, aha! So we can't use one at the same time. We have to do both. We have to compare. But we can't use one at a time. We have to look at both of them at the same time. So if tree A and tree B are both null, well, that's equal to each other, right?
Yep.
So nothing is equal to nothing. So return true. They're equal. True. And actually, this makes it really easy for the next two cases because they're just like the ones that we saw above. So else if we have if tree A exists but tree B doesn't, then they're not equal, right? We have nothing on one side, we have something on the other. They have to have the exact same shape, so they can't be the same. So it's impossible for them to be the same if you've got something on one side and nothing on the other. Okay?
Yep.
So otherwise, oh crap, they both exist. Now what do I do? Well, if they both exist, well, let's take a look. If so let's see, tree A dot item. If tree A dot item dot equals tree B dot item, right? What we have to do is now check see if their items are actually equal to data. And if so, we got to handle that. But if the items are not, if the data is not equal, return false. They are equal though. Well, okay. So they both exist. They have the same items, but now, and we're comparing by starting at the root for both of them. So now we gotta check if the rest of the trees are equal. So in which case, I'll return equals tree A dot left, comma tree B dot left. Ask if the left subtrees are equal, and ask if the right subtrees are equal.
Oh, you put left and right there. And
Yeah,
B
I did.
Twice.
I did.
You also put B twice.
I suppose I did. So here we compare the left subtrees with each other to make sure they're equal, and then we compare the rights to each other to make sure they're equal. Make sense?
Yep.
Okay. Now what? Sorry? Write a method that returns which characters occur in a string. Sorry, that returns what characters occur in a string and how many times each one occurs. So here, we're gonna calculate. We're gonna look at characters. So public static map. We're gonna count what characters occur in which string and how often each one occurs. So map character to integer. Map is equal to new hash map. Okay, and now for car letter in Word, but you can't iterate over a string like that, so I'm going to do two car array. Or I can't remember if it's 2 car array or 2 character array.
I just say it's char.
Yep, it's 2 char array. 4 letter in 2 char array. If the letter hasn't been seen yet. So if map dot contains key, if maps dot contains key letter is not true, then that's the first time we've seen that letter. We've seen it once now. So map dot put letter 1. Otherwise, if we hit the else, that means we've seen it before. So in which case, we want to say int prev, the previous count is equal to map.get letter. And then map.put, we need to update this because it's an integer. So map.put letter prev plus 1. And there we go. And then that's it. Return map. The question on the exam will be about as difficult as this one, which is not that difficult. We can also shorten this quite considerably by just simply doing this. We update the letter. We update the count of the letter to be whatever the count was plus 1. All right. I'm going to skip this practice question because it's not really relevant for here, but... All right, what are collisions in hash tables? Why do they occur and how are they handled? So what is a collision?
When two items have the same hash code.
Not just the same hash code, but they end up at the
Well,
same
yeah.
index.
Yeah.
When 2 items get hashed to the same index. So they occur because you've got too many, because you have a limited number of indices and an unlimited number of possible keys. So what are some ways to handle them?
Well, one option is to put it in the next available index.
And what is that strategy called? Anyone?
The parking garage method?
It's called open addressing.
Okay.
Open addressing, and specifically if you're going to put it in, open addressing means look to the next available space. And if you define next as like the immediately adjacent spaces, that's open addressing with linear probing. You can also do open addressing with quadratic probing, which means you look one space away, then one space away, then 4 spaces, then 9 spaces. Is there another method?
Yes, you can also use a linked list.
And what's that method called? It's got 2 different names that you can use. Both are valid. So so that method is called chaining or buckets.
Mm.
So hash tables with chaining or hash table with buckets, right? So everything gets put into a linked list at that index, or we call that linked list sometimes a bucket.
Would you accept bucketing?
Yeah, sure. The main thing is, describing what they are is more important than the name, but I would like to know what the names are, which is pretty easy to do when you have the internet right in front of you.
Yeah.
All right. What is the worst case runtime for insertion and deletion algorithms of a binary search tree and why? So what is your worst case for big O's for binary search trees?
Log in.
That's your average case.
Mm.
O of n.
O of n. So how could we get an O of n in a binary search tree? Let me draw an example. So question, Q is what? Is Q before T?
Yes.
The quick, brown, fox, jumps, over, lazy, and then dog.
Left of fox.
Mm-hmm. Conveniently, a great example of an unbalanced tree. Now, this is unbalanced because each time we would look for an item, we are only eliminating one thing from our search space. In a binary search tree, what we would want to do is eliminate half the search space with each step. But here, it's just a funky looking linked list. So, another example is just simply a tree that looks like this, where like maybe you inserted the numbers 1 to 1 million into a tree, and it just looks like that. In which case, it's just a linked list that uses extra space. So, now in practice, though, most of the time we use something called a balanced binary search tree, which basically means, hey, if things get too much out of shape, then we rebalance the tree. And it takes log n time to rebalance a tree. So log n to add plus log n to rebalance is 2 log n. So it ends up being a pretty successful method of doing that. And the way it does it is with something called the rotation, which raises and lowers the levels of the subtrees, and that's a constant time operation. All right. So, any questions about the exam?
I'm just expecting a similar, programming question like what you showed with the maps.
Mm-hmm.
That's it. Everything else is just based